You ever really stop and think about it? You hit play, and a 4K movie just streams perfectly. Or you're on a video call with people from three different continents, and it just works. It honestly feels like magic, but it's not. It's this incredible, invisible engine of engineering. So today, let's pop the hood and see how this thing actually works. So, how does it all happen? I mean, really, how does a tiny piece of your email or a single frame of that video navigate the entire globe through this chaotic web of cables and routers and still arrive perfectly intact? Well, the answer isn't some single silver bullet. No, the internet as we know it is built on the really elegant solutions to three huge, fundamental problems. You just don't see them. And in this explainer, we're going to unpack every single one. Okay, problem number one, the universal language problem. Just think about it. You've got iPhones, Android phones, Windows PCs, Linux servers, smart fridges, you name it. An absolutely mind-boggling variety of hardware and software. How in the world do you get them all to communicate without it just becoming complete and utter digital chaos? The solution is a beautiful concept called a protocol, and you can just think of it like grammar for computers. A protocol is a super strict set of rules that everyone agrees to follow. It doesn't matter if you're a supercomputer or a smartwatch, as long as you follow the rules, you can talk to anybody else who's also following the rules. Now, when engineers were first figuring this out, they came up with this really detailed 7-layer theoretical blueprint. It's called the OSI model. But in the real world, the internet was actually built on a much more streamlined, practical 4-layer model called TCP/IP. This is the one that's actually running the show. It's the model that powers our digital lives every day. So let's see how it works. Okay, so this whole process of sending data is called encapsulation. And honestly, the best way to think about it is like preparing a package for international shipping. It all starts right here, at the application layer, with the actual thing you want to send, your data. This is the content you're putting inside the box. Next up, the transport layer wraps your data in something called a TCP header. And this adds a totally crucial detail, the port number. Think about it. Your computer is running dozens of programs at once, right? The port number is like the apartment number on the address. It makes sure this data goes to your web browser and not, your email app by mistake. Then comes the internet layer, which adds the IP header. Now, this is the big one. This is the main mailing address for the whole package. The full street address of where it's coming from and where it's going on the global internet. This is what routers all over the world are going to look at to forward your package along its journey. And finally, the host-to-network layer adds the last wrapper, turning our package into what's known as a frame. This includes the local hardware address, or the MAC address. You can think of this as the address for just the very next step, like just getting the package from your computer to your home Wi-Fi router. That's it. From there, the router takes over and figures out the next hop. Okay, so we've solved the language problem. Everyone's speaking the same language. But now we have a whole new issue. The physical world is, well, it's messy. Signals get distorted by electrical noise, packets can get dropped by a busy router, they just disappear. So how do we guarantee that the message that arrives is exactly the message that was sent? The solution here is a 2-step process called error control. It's actually pretty straightforward. First, you have to be able to detect if an error even happened. And second, if you find one, you need a way to ask for that data to be sent again. For detection, one of the most common tricks is the cyclic redundancy check, or CRC. It's really clever. Through some math, the sender creates this unique check value from the data and attaches it, like a digital fingerprint. When the receiver gets the data, it runs the exact same calculation. If the fingerprints match, the data's good. If they don't, it means the data was corrupted along the way. And that brings us to step 2. Retransmission. This is handled by a protocol called Automatic Repeat Request, or ARQ. And you can think of it as a very polite but very strict conversation. It uses acknowledgements, or ACKs, and timeouts to manage the flow of data. Let's see how it does it. So the simplest version is called Stop and Wait ARQ. In a perfect world, it goes just like this. The sender transmits a frame of data, and then it just waits. The receiver gets it, sends back a little got it message, an acknowledgement, And only after the sender gets that ACK does it send the next frame. Simple, clean, and reliable. But what if that acknowledgement gets lost? What if it just vanishes? Well, the sender is smart. The moment it sent that first frame, it started a timer. If that timer runs out before an ACK comes back, the sender just assumes something went wrong, and it resends the original frame all over again. It's this simple timeout that makes the whole system so incredibly reliable. So stop and wait is reliable for sure, but it's not very efficient, especially over long distances. And this formula here, don't worry, no math test, it shows us exactly why. See that T prop? That's the propagation delay. It's the physical time it takes for the signal to travel. And because it's in the bottom part of the fraction, as that travel time gets longer, the overall efficiency absolutely plummets. The sender ends up spending most of its time just sitting there, waiting. And this inefficiency is precisely why engineers invented much more advanced protocols. All right, let's move on to our third and final problem. And this one is a fascinating paradox. To make a network reliable and robust, you build in redundant paths. So if one link fails, traffic can just go another way. Simple, right? But what if that very redundancy, that safety net, could create a catastrophic trap that destroys the whole network? So what happens when a certain type of message, called a broadcast frame, gets caught in one of these loops? Well, you get what's called a broadcast storm. The frame is copied and forwarded by network switches endlessly. It multiplies exponentially until it's a raging flood of data that consumes 100% of the network's bandwidth, crashing it completely. We're talking seconds. The solution is this incredibly clever protocol called the spanning tree algorithm. You can think of it like all the switches on the network getting together for a meeting. They elect a leader, they map out the entire network, and they figure out exactly where all the dangerous loops are. Then they just logically block enough ports to break every single loop. Take a look at this. It's a simple network with 3 switches connected in a triangle. That's redundant, which is good for reliability if one link goes down. But you see the problem, right? It's also a perfect, deadly loop for a broadcast frame to get trapped in forever. And here's the magic. The spanning tree algorithm has identified that loop and put one of the ports into a blocking state, so no traffic gets forwarded through it. And just like that, the loop is broken. But, and this is the key, if one of the other links fails, the protocol can reactivate that blocked port in a matter of seconds, restoring the connection. It is truly the best of both worlds. Totally loop-free and still super reliable. So when you pull it all together, what you start to see is this hidden elegance. The completely seamless, simple experience we all have using the internet is only possible because of decades of brilliant engineering solving these deeply, deeply complex problems behind the scenes. So to recap, we had the problem of total chaos with trillions of devices trying to talk. And that was solved by layered protocols like TCP/IP. We had the problem of fragile data traveling through a messy world, and that was solved by robust error control systems. And finally, the self-destructive danger of redundancy, solved by smart algorithms like spanning tree that create a safe path. These solutions are the invisible engine powering our modern connected world. But here's the thing to think about. They were largely designed for a network of stationary computers connected by wires. As we look to the future, to massive global satellite networks, to billions of tiny Internet of Things devices, it really begs the question, what's the next great invisible problem that we need to solve? And what brilliant solution is it going to inspire?